Hello everyone, my name is Luke Hanks, and this is my Lab 4 video for Physics 2212. So the purpose of this lab, basically we're just going to talk about the loop rule and the node rule when it comes to circuits, and then we're going to examine how resistors, capacitors, and batteries operate in series and parallel. So the physics principles that we use here, we already stated the loop rule and the node rule, but as for equations, we have the change in voltage of the capacitor plus the change in voltage of the resistor should equal to be 0, and then we have Q over RC plus dQ over dt equals 0, which is just a differential equation talking about the rate of change of charge over time for a capacitor. And then the final equation we just use to calculate the time constant. So the first part of the lab, we did a simulation with a series circuit. And here the point is we're just going to talk about how charge is conserved and voltage as well. So first thing we had to do was just predict the current, and the way we can predict the current, we just take the total voltage and divide by the resistance, and that calculation was 0.0204 amps. And the actual current the simulation showed was 0.02 amps, which is the same thing practically. And so I found that flipping the ammeter also had no effect. So for the next part of the series, we had to remove one of the ammeters and replace it with a voltmeter. And so when one of the ammeters is removed, the other ammeter reads 0 amps because there's no current flowing through it, but the voltmeter is going to read 3 volts because there's a potential difference across the wires of 3 volts. And then the final part of the the series portion. So we were talking about the conservation of voltage here. So the total voltage difference across all areas was found to be 0. And so the way we found the different resistances for each of the resistors was we just divided the change in voltage by the current. And so you can see on the right just the different delta V's I found between each of the locations. And each of the locations just corresponds to a different resistor or something, a part of the circuit. And so as you can see the graph on the right, from A to B, we just have the total voltage of the batteries, which was 3 volts, and then with each of the steps across the resistors, the voltage decreases back down to 0. So the next part we had to do RC circuits, which is just resistor and capacitor circuits. And so the first thing we were talking about was just charge time for a 10 ohm resistor with a capacitor. And so the charge time I found was 4.41 seconds, and the discharge time was 9.36 seconds. And the charge time for a 20 ohm resistor was 7.05 seconds, and the discharge time was 18.39 seconds. And so I used that data. I used the data of discharging a 30 ohm resistor along with a capacitor to calculate the time constant using the equation we found, or I showed in the very beginning. And the slope was calculated to be negative 1.67, and so that value is equal to negative 1 over RC, and RC is the time constant, so that calculation just results in RC being 0.598. So what if you were instead doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So a real ammeter would have some resistance to it, so voltage would change across ammeters, and you have to account for that. And then the next what if question, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So the prediction is not going to happen in real life because the battery has some internal resistance to it, and it would take longer to charge the capacitor in real life. And thank you, that's my lab.